And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment.
The first people who did these experiments, and these experiments of, crude experiments of this kind were first performed almost 50 years ago, or more, 60 years ago. Those people were flabbergasted.
To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
This is just to break down your prejudice that says a particle is a particle. Now you got to understand it's a particle and a wave.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense.
You got to understand it's a particle and a wave. Now that you've taken that leap, let's get one step closer to the reality. It ain't either of those either. And it's both at the same time.
But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other.
We did these experiments, and we got certain results. And in the light of these results, we asked a question of the form, gee, which path could the electron have taken through this two-paths apparatus? And if there are two options like that, it's just a matter of standard classical logic, there are four logical possibilities. A, B, both, neither, okay? We went through those possibilities one by one and designed an experiment in each case to test that possibility. And the answer in each of the four cases was negative, okay? It doesn't go through root A. How do we know that? Because when we put in a total of nothing box in root A, it has an effect on this particle. But total of nothing boxes don't have any effect on particles that pass through them. It doesn't go through root B for the same reason. It doesn't go through both roots because if we stop the experiment in the middle, we always find it either on one root or the other, but not both. And it doesn't take neither root because if we just block up the two roots and leave everything else open, nothing gets through. So we can systematically, piece by piece, eliminate all of the four logical possibilities, okay, given the assumption that it makes sense to ask the question, which route did it take? That's how we're forced into a position, gee, the only thing left to do here, it's analogous to, think about the case of inquiring into the marital status of the number 5. Somebody says, gee, is the number 5 married? You say, no, that's not the right thing to say. The guy says, I see, number 5 is a bachelor. You say, no, that's not right either. The guy says, well, what else is there? You say, look, the deal about the number 5 is it's not married, it's not a bachelor. That's not a logical contradiction. The trouble here is that the whole question of the marital status of the number 5 is a question that can't sensibly be raised. That's what we're finding out about these particles. We say, did it take root A? We can eliminate it experimentally. Did it take root B? We can eliminate that experimentally. Did it take both? We can eliminate that. Did it take neither? We can eliminate that. All that leaves us with is going this route that we go with the number 5. Oh, I see. Although in this case it's astonishing. With the case of the number 5, it was easy. What this must be telling us is that it somehow fails to make sense even to raise the question in a situation like this. Which route did the particle take?
Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So the electron is very peculiar. The electron is very peculiar in the sense that when you are not looking, electron can be here, can be there, or can be over there in the corner of this room. It can be all over this room, so to speak. But whenever we look, this is the strange thing about these electrons. So whenever we look, we always find them to be in one particular Geiger counter, although we may have a room full of Geiger counters. We never hear the Geiger counter sticking all over the room. This is the fundamentally important stuff about the electrons.
It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.